Thank you, everybody, for attending the March AusBIAS meeting. I'd like to acknowledge the traditional owners of the land on which we meet today. In my case, it's the Gadigal people of the Eora Nation, and pay my respects to the elders past, present, and emerging. I am delighted to introduce Nick Condon, and I'm going to read his bio. I did bully him into writing one for me by telling him if he didn't write one, I would write it on his behalf. And he took that threat seriously and sent me one. So Nick is a senior principal imaging scientist at the Institute of Molecular Biosciences Advanced Imaging Platform at the University of Queensland. That's really long, Nick. You sound like a big deal. He completed his PhD in cell biology using advanced light microscopy to study macrophage cell surface behaviors, including how they eat and drink. Nick works collaboratively across diverse disciplines, publishing with experts in dentistry, animal vision, mammary gland biology, peptide chemistry. The list goes on and on. I'm not reading all that. He's actively engaged in building capabilities and research infrastructures that empower scientists across the life sciences. And he is going to talk to us today about some exciting research infrastructure. So I'm going to mute and turn it.
Are you okay? It's amazing what ChatGPT knows about me. So thank you for the opportunity to present today. A little bit of context. I've been invited to give a talk to the Global Bioimage Analyst Society's seminar series on infrastructures. And this was kind of a half practice run, but also one that's at a more suitable time for the Australian audience, because I think it's at 1 p.m. Europe summertime next Tuesday, if you haven't seen the invite. But the title of my talk today is Big Data Infrastructure Strategies for Image Analysis in a Core Facility. There we go. So I'd like to as well acknowledge the traditional owners of the lands which I'm coming from today, which is the Yagara and Turrbal people. I pay my respects to ancestors and their descendants who continue cultural and spiritual connections to country, and we recognize their valuable contributions to Australian and global society. Because this is going to the global audience, the University of Queensland is in Southeast Queensland in Australia, which is on the East Coast. And we have 57,000 students, 20,000 postgrads, large alumni community, and we are kind of research focused as well as teaching university. The Institute for Molecular Bioscience, where I work, has 36 research groups with over 500 researchers and over 150 HDR students, and we have a large number of industry partners. Collectively, the Institute falls into kind of four main centers: the Center for Population Genomics, Disease Genomics, Superbug Solutions, Cell and Biology of Chronic Disease, and the Center for Chemistry and Drug Discovery. And these groups work on a whole variety of different diseases, conditions, and research areas, which means as a facility, we get to see lots of different things and work on lots of collaborative projects like what Pam was talking about in my bio. So we have recently renamed the Advanced Microscopy Platform. We have 20 microscopes. We have 220 users in the last 12 months. We have approximately 20 analysis servers, which I'll talk about. And we have, do lots of user trainings and projects with our current 2.8 FTE. I just received confirmation the job ad for a new senior microscopist will go out on Monday. So if you're interested, keep an eye out for that. So we have lots of different microscopes. Some of the technologies that we have and how they're used include things like stereo microscopes for developmental biology, wide field systems for slide scanning and cell biology based things, developmental biology on confocals and spinning disks, and we have a lattice light sheet that mainly for cell biology research. The data sets that come off these are really different. So the stereo microscope is usually used for multiple embryos at a time lapse, tile scans, 1 or 2 colors, and they can be up to 200 gigabytes per organism. The wide field systems, slide scanning, again, it depends, but it's a different shape, different format. The confocal similarly can do time lapse and tile scans as well. We have two spinning disk systems. One of them is the Dragonfly. This is one of the big data producing systems. We have users making very large tiles, Z stacks, time lapses with multiple embryos where we can see over 1.5 terabyte files being produced pretty routinely. And we have a lattice light sheet 3i system, which is single or dual color 3D time lapse systems plus a lot of processing. Storage isn't an issue for us. We have solved that with the university's platform. And the issue that we see now is this kind of flow of data through the system from the microscope into analysis and to share and publish. So the University of Queensland has a petabyte scale storage system called Research Data Manager. It's a one-stop shop for managing the data sets and the research data that meets both FAIR principles and the different governance and compliance standards, both at the university and at the federal Australian standards. It supports logging in with obviously the university credentials, but it's built for collaboration, so there's many ways that we can log in with industry, LinkedIn, things like that as well. So it's quite nice. It's project-based, which means we have the ability to add and manage collaborators. We can add things like animal ethics, human ethics, grant codes. We can link digital research notebooks. We can link different storage allocations to it as well. And soon we're linking in our laboratory inventory management systems for reagent and resource tracking as well. The way it kind of works is it's the fabric underneath is the storage the data actually lives on is an IBM product called Spectrum Scale or GPFS or ESS. It undergoes name changes every couple of years. And it has the management and the synchronization is controlled by a HP product called the Data Management Fabric version 7. That's the latest one. What does this mean, though, for this kind of audience is we have two major vendors that we've smashed together to make this product. So while it's a really nice product and works really well, it's taken a fair bit to get them to work together. But when you make a project and you have a collection of data, it gets its own identifier code, and that can be referenced by all different tools, such as the microscope booking platform and facility management software. It can be linked to external transfer networks. But the real benefit of the data infrastructure and the way it's shaped is it's a tiered storage system. So we have essentially multiple copies of the data at different locations. I say copies in inverted commas because it is technically the one file, and that's what the DMF7 product manages. But what we have at the microscopes and close to the instruments on campus is the super high speed ingest systems for getting the data. And then as you go out to the backups and offsite locations, we move down to the kind of warm, not as fast storage, and then obviously tape and things like that that can be filed away. So the storage system meets all the requirements, as I said, but the users don't need to worry about where the files are, whether they're on tape backup or not. That's all handled by this collaboration that we have with the IBM and HP products. Once we've got data and we've have it in the storage ecosystem, we can connect these to the outside world. So we can take a storage allocation and share it with a DOI through UQ's eSpace platform that can have license attributes to it and software required and versions and all that stuff that can be added to it. And we can also take the data off to collaborators through tools like Globus, through S3 buckets, and with RNet. They're all connected in the back end so that we can share this data around and publish it. This is great if you're a computer scientist, but most biologists and the users in our facility, it can be scary. It's really big data. It's in different locations. We're talking about network drives and storage and cloud access. And so how do we as a facility kind of begin to think about what tools we need to build that will address like the challenges that we see around moving the data, how usable the data is, and is all of the things that we're doing reproducible? We have kind of a high level tool design principles that we try and adhere to that help shape the things that we're building in our kind of the architectures. We don't want to move the data as more than we have to. So we approach that by moving compute to the data rather than copying it from one location to the next and moving it around all the time with the users. We try and minimize duplication so that we're not copying the data too much. We try and provide standard environments. So when we talk about our virtual machines, we build them all the same way to make it kind of familiar. We want to make sure that we're capturing metadata early and not kind of relying on the users to fill in some lab notebook weeks later, because they don't. And we want to automate where possible because we have all these resources with effectively 2.8 FTE. This should come as no surprise to our users, or sorry, to the people in this meeting, that the general flow for microscopy is plan some experiment, image it, analyze it, and then hopefully share it and publish it. So how do we build tools at these different steps along the way? Well, at the microscope, we tend to always tune up the computer and try and fix some of the bottlenecks there they're pretty poorly spec'd when we buy them from the vendors. We have pretty average user behaviors sometimes, and we want to help capture metadata beyond just the hardware settings that's in the file. So how do we create a better user experience at the acquisition PC? Well, all of our users log in with their own credentials. That means that we know exactly who's using the microscopes. We can get information about, is it developmental biologists? Is it cell biologists? Should the microscope be set to 37 degrees or 28 degrees? It means that when a user logs in, they get their copy of the settings. So if another user changes something, it shouldn't affect them and their sessions. And it lets us map their RDMs automatically because I know that user X logged in and I know what RDMs they have available to them. On the actual PC itself, we tend to rip out the SSDs that the vendor provides and put in NVMe rated storage. This means that we can have super high speed, like 100 gigabit IO, up to about 30 terabytes. And that allows us to generate the data and transfer it off without it affecting the overall user experience or crashing the software, for example. And we also have lots of scripts for automation. So we auto delete files so that we don't have to go to each machine and worry that it's not got enough storage for users. If the script doesn't work, you can email us, just makes it convenient. So we don't have to go routinely to the microscopes. They kind of cry for help when they need it. What we've realized is that you can't optimize for things that you don't know about and you don't see. So we have to kind of think about, well, is the instruments is there enough computing resource allocated to it? Because we find like if it's crashing all the time, it's usually taken more than one time for it to crash for the users to come to us and complain. So we want to make sure that we're provisioning enough RAM and memory and things like that. Transfer speeds, getting data off the instrument, an issue. And what kind of samples and settings and that are being used so that we can better plan the session. So we mine a lot of data. Some of the things that we can do with some of the data that we mine is, are the computers resourced enough? So whether it's a server for analysis or the microscopes, we have, it always reports back every minute to a database that, so-and-so is logged on. They're using either 25% of the RAM, 50% of the RAM, 75% or above. And we can track that. So if we have a server that's got 2 terabytes of RAM and no one's ever hitting above 50% of that, well, we can probably dial it down and have 2 and better allocate that resource. Are people staying at the microscope or server and working interactively, or are they setting up something and running it, or are they accessing it remotely? And we can track things like mouse idle time and things like that to get an idea of how behaviors are being run. And are people running analysis on the microscope PCs when we maybe have offline licenses to do that, or maybe we don't, and that they are running it there and we can kind of use that to guide purchases elsewhere. On the experiment front, though, the acquisition metadata alone, so the objective, the laser intensity, things like that, doesn't really provide enough experimental context. And sometimes accessing the digital research notebooks from the acquisition PCs can be a bit cumbersome, whether that's because it's an old Windows 7 machine that's not on the network, or because when you log into it, you need to use MFA and you might not want to be using your phone in the lab. We have to kind of think about that. I also, as an image analyst, see some pretty poor file naming conventions that are just trying to embed as much information in there, which isn't good for the file systems, and just it's not really what we should be doing. And I'm obviously aware of projects like Founding Guide, GROP, LIMI, and REMBI, where they're providing guidance on the various metadata fields that we should be recording if we are to put them into image repositories. And some of these public image repositories have already adopted the REMBI standards, which we need to then get our users kind of up to date on. So if we're not capturing metadata at the microscope around what's the sample, how is it mounted, when did you add a drug or something, it probably won't be captured. And then we rely on memory, and it's not really ideal. So we set about to try and make a tool that could capture information about the experiment, make it interoperable into the digital research notebooks that we have at UQ, and kind of prompts the users by describing their experimental data, such as the sample type, how it was labeled, what project it belongs to, because then we can get information about the ethics and things like that. And this will kind of hopefully align with the needs of the community, and as the researchers prepare their data sets to go into the repositories. I've already had 2 group leaders come to me going, what's this stuff that they're asking about? So we need to start getting some traction on this. So I built a proof of principle tool to begin curbing some of these user behaviors, and we called it Remind. It's the recommended metadata interface for documentation. It's a lightweight GUI to just prompt users to start thinking about entering their data of their imaging experiment. It can output currently it's text, XML, JSON, and CSV, or tab delineated for Amero, in both structured human readable and machine readable formats. This is what it looks like. So it's just a little Python window that you can run. You can enter information. You can currently drop like a CZI or a Leica file on it to populate some of the extra fields as well. And you can fill in just general notes. And that can be stored alongside the data for future kind of when we go to ingest it. One of the side things that we noticed was that the outputs that can be reloaded as templates, because we wanted to make it easier for users and have them not fill out the same stuff. But also because it's just text-based, it's searchable. So while like your operating system, Windows or Mac Searchlight doesn't really let you search a CZI file for its metadata, this is searchable and will help. I think of the group leader who's looking for the data set that honest student had and is can help. And if we can get the group leaders on board, then that's a big stick to make the users use it. In the future, though, we could use this to orchestrate moving the data. So UQ already has a tool called Pitchy, developed at the Center for Microscopy Microanalysis, or CMM, that can say this booking associated with a RDM project then moves the data. So we could leverage that as well with this. And also, like, I want to move away from free text fields and have ontologies. So I was talking with Greg Bass late last year about this. But obviously, we want to look at the data as well. We want to visualize it. We also want to quantify it. So how do we do that in the age of big data? Well, we've moved 100% to virtual servers because these provide a really valuable solution. The reason they are useful is because they're going to live in the data center, which means they're going to be fast connected to the network and have 100 gigabit network cards usually. They can fit more CPUs in them and CPU cores, which means you have more GPUs available and you can have more memory sticks of RAM, which I know is getting expensive. So, but the other benefit is they can be accessed from anywhere. This is a kind of old photo now, but it proves the point that you can access this on a kind of mobile phone connection, which means it's really good for traveling and working from home. So one of the reasons we've done this is that we've moved the compute to the data. So instead of having like in the imaging facility, the big powerful workstations, now the data lives in the data center and the compute lives in there. This enables us to also have consistent environments. It's remotely accessible, entirely scalable, and it's pretty easily supportable. So how can we configure these? And if you're not familiar with the virtual machine environments, the following slides will kind of go through some of the technologies. So if we imagine that we have one server that we call a host, and it has some kind of resource allocation, we can divide that evenly into just 3 different virtual machines, allocate equal cores, RAM, and one whole GPU to it. And that's relatively straightforward. And then you can put different software and things like that on those virtual machines. You can also have different shape virtual machines. So here I've slightly changed the amount of the host just to make it easier. But we might have 2 medium-sized virtual machines and then one kind of bigger one. And they can have different RAM allocations, or they could have different CPU, or they could have different GPU allocations. And you might be doing that because you might have like a specific software that you need that needs more memory. Say Lightsheet might need a bigger box. It's also possible to carve up the GPU and virtualize that with specific GPUs. And so if you have enterprise grade cards, and buy the relevant licenses from NVIDIA, it is possible to chop them up. So they have this thing called virtual workstation. It used to be called Grid. Again, software companies renaming stuff. But you can chop up one GPU into different virtual GPUs. And you can also deliver multiple virtual GPUs to one VM, or you could take 2 different physical GPUs and have virtual chunks from both of those presented into one virtual machine as well. So this lets you kind of really configure workloads. So whether you need to parallelize something, whether you need more memory for a deconvolution job, it lets you do that. And the licenses that you pay get you these drivers that handles all of this. There are some limitations. It's not a perfect system. But basically, firstly, it costs money. It's not that prohibitively expensive. I think we pay about $1,000 a year. There are defined sizes. It's not infinite with how you can chop up the GPU. So that can kind of limit what shape VMs you want to make. Another limitation is that each physical GPU that you have that you chop up, you have to chop it up into the same size chunk. So if you have an L40S with 48 gigabytes of VRAM, you can't say have a couple of 1 gig GPUs, a couple of 4 gig GPUs, and a 6 gig, right? You have to evenly chop it up. And also, not all of your shiny, expensive NVIDIA GPUs work. They have to have the virtualization drivers and components. So something like the A100 doesn't, but the A40 does. So just keep that in mind. You can also do non-symmetric setups. And this is what we have on one of our servers. It lets us run kind of 8 small VMs with moderate resources allocated. So it's got 6 gigabytes of RAM, or VRAM, sorry, on the GPU and 128 gig of RAM. This is something that we'd normally throw all our open source software on, and they have enough GPU that they can do like a cell pose or something. And then we have 2 larger VMs that have a bit more memory, a bit more cores, and they get a whole GPU each. The reason they get a whole GPU each is because we have people doing deconvolution on tiled data, and rather than having to chop it back up, we have enough memory to push all of that in. Some of the benefits that we see as a facility doing this is greater resource flexibility and availability. So we can clone the machines, which means we can deploy them quite easily for like a workshop or if we have a change in software. It also, because they're virtual, means that we don't need to have space in the facility to host all of these analysis computers, right? But as a warning, making too many of these can become a bit difficult to manage. We also cost recover on these, so users pay. Because they're virtual, we have other people from the university and other people from outside of the university accessing them and paying. And they're quite accessible remotely. So I look at some relatively old data now, but when we look at income on the machines by outside of hours, it's about 25% that we're getting, or 20% getting in the income, which is quite nice. Another benefit that you have is that you can kind of oversubscribe these resources. So I described this machine that we run as the left part of this breakdown. The what we also have though is a further 8 VMs that are copies of these other small ones that exist but are just turned off most of the time. So what we can do is we can book out the 2 bigger VMs, turn them off, and then turn on these, and we have 16 VMs for a workshop. You might notice that we are leaving kind of resources on the table if we do this. So one whole GPU tends to just not get used. That's because there isn't a 9 GB profile, so we don't have that option. And even if we had an 8 GB profile, what that would mean is we would actually have to have 2 copies. So a 6 gigabyte profile, small VMs that we usually run, and we would have to have 16 copies of the 8 GB profile. You want to run these profiles off, or these virtual machines off the hard drive in the host. You don't want to be running somewhere else because you'll experience kind of slowdown, lag, and stuttering. And these servers only have a 16 terabyte drive. So if we have 32 computers on there, it's not very size efficient. Other considerations are, well, there's a lot, but the main ones is like software licensing. So servers tend to not have a lot of USB ports. So think about network licenses. We're starting to test a USB hub that virtualizes the USB across the internet into the VMs. Some software just refuses to run on the server. And do you have the licenses for the hypervisor and the virtual workstation? Access control. These aren't a physical computer you can walk up to. So if someone's not booked it, you want to have a way that you can kick them off because they could be coming from anywhere. And also, how do you limit the number of users? So while you can have dynamic VMs, we just have static VMs. So they're just they're a virtual box that someone books and they get that resource. We're not dynamically spinning them up and down. And then you also have to think about like what level of training is required and what's the computer literacy of your users. So for a long time, we actually had on the desktop, this is the virtual machine, because people didn't quite understand the computer in a computer. And then how are you going to help them learn these things? Is there policies around at your institution? But sometimes as well, you need bigger computing, which is the HPC. So this is kind of when it goes beyond the interactive workflow. We have kind of 2 layers at the University of Queensland for HPC. We have AusBIAS, which is the kind of flexible, more expert user. And then we have our image processing portal, which provides a more guided experience. This audience probably doesn't need to know why we need this. We have lots of camera-based microscopes that make a lot of data. We have users that are rapidly producing data in very short term or kind of over the duration of a project. It's not uncommon for, multiple tens of terabytes to be produced. The map of how things are all connected can be a bit daunting for the users. So we want to not have them rely on command line to push data back and forth between locations or anything. And as I said earlier, we want to avoid that anyway. And also, why is it needed? Well, it's free, and having free compute and resources is always good in this environment. And also, bigger cameras and things like light field are coming that are going to make a lot of data. AusBIAS is our kind of UQ branded on-demand tool. If you haven't heard of Open On Demand, it's a kind of like a web interface that lets you create jobs, execute and delete them, manage stuff, all from a web browser in a very nice kind of GUI. You can launch dynamic Linux desktops of various sizes and resource allocations. So this is what one of those desktops looks like. And we run the old characterization virtual laboratory stack of software. Obviously, the software has been updated, but that's just how we run it. So we have most of the open source image tools are on there. You can also run Jupyter Notebooks, VS Code, a terminal in the cloud, in the browser, all that as well. And one of the nicer features is that we have this ability, you can take a Slurm job ID, chuck it in, and it shows you over time all of the resource allocations that, how much you used versus how much you asked for, and that can kind of train users. But obviously, I'm more interested in the image processing portal, which is a tool that I helped develop with RCC, or I helped design and got them to build it. But this is a GUI that lives in the browser for the GPU cluster. It lets you explore files, move them, copy them, rename them, all that kind of stuff without pulling it via your desktop. It'll create all the commands and send it off to the cluster. We've got things like file conversion, deconvolution, stitching, and macro execution as well. And it uses wizard-like workflows to build up a job and then submit it. And it provides a receipt at the end that says, this is what you did, which will kind of become apparent why that's useful later. A quick video, if you haven't seen it, is this is what it looks like in the browser. You can navigate files and folders. You can see the different collections that are available. You can spin up desktops, and we strip away some of the, we try and strip away some of the nuances of how many virtual CPUs and things like that you need. You can do a deconvolution job. It uses microevolution. Obviously, Vincent's here at the moment. We're exploring putting Huygens in there as well, because microevolution no longer exists. You can see the jobs, you can see job histories, we can configure it with different things as well. So I mentioned before this receipt or a record. So because we know everything that the user submitted, we can send it to them in an email that's kind of human readable, and we can store it in JSON that's then machine readable, where we can use that to reconstruct a job or reapply settings for the job. And also because we're using Slurm on the HPC, we get the output files that provide like a log of all the things that were done while it was running. We have lots of groups using it, generally from the Lattice, because that's what we built it around. So yeah, this is where we're at now, and I've purposely chosen the bumpy, rocky road because it's kind of reminds me of the project, but we have a path towards automated data management from the instrument to analysis, and then we have the ability to publish that data sets out. We've built a proof of concept tool for capturing Rembre-like metadata to ensure kind of readiness for disseminating these data sets. We have solutions for various levels of accessible compute infrastructure, whether that's interactive Windows boxes, we have the open on demand ones, and we have this HPC. Everything's scalable. We're trying to build out centralized workflows. Most users are doing similar things. So we have tools for batch processing, batch cell posing, things like that. And we have mechanisms for reproducible analysis. All up, this tends to have a significant reduced support burden with our approaches, but it kind of creates new problems for ourselves as well, which it keeps us busy. I still want to solve a kind of major issue, which is capturing analysis steps used during interactive sessions. So when we have like the Windows remote VM that someone logs into, we don't really have a way to capture what they did there. So we could at launch of Fiji run record, but that's just going to be a mess. So how do we try and tidy that up? Whether that's through training or whether we help, have a tool. And we need better ways to link out the ontologies into these tools so that we're not relying on free tech because users can't be trusted. There's a lot of people, too many people to name. We have the microscopy staff, and Deb was heavily involved in some of the tools, and her partner. IMB IT, obviously heavily involved with shunting the data around the building, the Research Computing Center, with development of some of the portals and RDM backend. The library manages RDM as well as a dedicated team. Central ITS for some of the other things. Our booking platform team support, and obviously all the researchers who come to me with all their problems. Lastly, a quick shout out. This open call for HPC and cloud-based solutions in image analysis in the Physical and Life Sciences special edition of the Journal of Microscopy is still open. It's extended until about the end of April. So I would encourage you, if you are interested in these type of workflows and are doing stuff in this space, submit something. Be great to see some Australian content in there. And I'm happy to take questions. I think there's some in the chat as well.